We now take a step away from the syntax and features of the shell programming language itself and focus on some of the support tools that are available in Unix for shell programmers. In particular, we want to focus on the class of utility programs that are dedicated to text processing. This class of programs is known as the filters. Oftentimes, when we are developing a shell script, we need to perform some text processing. Often we need to analyze the text that is produced by a program or is contained in a file, or we may need to present this text to a user in a user-friendly way. And there is a whole family of programs that are provided to us, mostly for use by programmers, that are catered to exactly this sort of text processing. These family, as I mentioned, is known as the filters. Let's have a look at them. We first need to understand what a filter actually is, so let's have a look at that. And a filter is a command line program that has the following properties. The first is that it takes standard input. Standard input means that it can read characters from the keyboard that the user types. Now, if it doesn't take standard input, then it can also read the contents of one or more files. In other words, standard input has to come from somewhere. It either comes from a file or it comes from a keyboard. And all these filters work the same way. If you specify one file on the command line, then it will read that file and use that as its input. If you specify several files on the command line, then it will read all of the files and use the contents of all of the files as input. And if you specify no files on the command line, then it will read the input from the keyboard. The second property that all filters have is that they perform some processing on the above data. In other words, whether the data comes from a keyboard or whether it comes from a file, that data gets processed in some way, and the different processing is what separates one filter from the next. Finally, the filter produces output based on that input. In other words, it produces output which is the results of the processing that it did in step 2. Now you might look at that list and say to yourself, well, surely all Unix programs are filters because they all adhere to those three properties. Well, that's not entirely true. So what I'll do is I'll show you first a Unix program that is a filter, and then I'll show you one that's not. Firstly, WC is a filter. Specifically, it does indeed take standard input or the contents of one or more files. I'll just prove that to you actually, because it is an interesting thing that you need to know about all filters. Let's examine how WC actually works. I'll do an ls-l in this directory, and I find a series of files and directories available. So I'll just do a WC, for example, of names.dat, and that is the number of lines, words and characters in names.dat. Then I can do a WC of star, and I get some error messages for the ones that are directories, and then I get the numbers next to ones that are not directories and a total at the bottom. And again, all of this is as you would expect. A filter will process a single file or it will process several files. Now the interesting thing is it will actually also process no files at all, which means that if you just type in WC by itself and press enter, then, well, it's just sitting there waiting. Now what's it waiting for? Well, it's waiting for you to type something on the keyboard. So I can do a little bit of typing here, do maybe 5 or 6 lines of input, 6 lines there, and finally when I've finished typing all my input, I have to type the special key on the keyboard that says to WC, and in fact says to all Unix programs, I have finished typing, there is no more to type. And that key is, do you know what it is? It's the end of file marker, which is Control D. So I type Control D, and WC completes its processing. And I found that I typed 6 lines, 15 words and 85 characters, which I'm sure is correct. The interesting thing that I wanted to show you there is that it is actually possible to get WC, and in fact any filter at all, to not take any input from anywhere besides the files. So you can actually just get input coming directly from the keyboard, or of course there's the other way of getting input, standard input, which is to pipe it from another program. So that is another way of getting input into any filter. So please keep all of those techniques in mind when you're thinking about any filters, because it may not be obvious that some of these programs can be used in this manner. So having said all that, let's now have a look at an example of a program that is not a filter. Well, actually most programs are not filters, and I'll show you one in particular that's very common that you know quite well, and that's the ls program. That is not a filter. And there's a very simple reason that it's not a filter. It's because it takes no input. It does not take standard input. For example, we can of course do an ls of star on the command line, and that works, but if we just do an ls by itself, we still get some output. It does not at any point sit there waiting for us to type something on the keyboard, nor can you pipe anything to ls. Well, you can pipe something to ls, but ls will completely ignore what you pipe to it. So in other words, ls does not ever take standard input. So a good way to test, I guess, whether a program is or is not a filter is to simply ask yourself the question, can I pipe information from one program into this program and have it use that information in some meaningful way? If the answer is yes, then it's a filter, and if the answer is no, then it's not. And filters are actually used to process the data produced by other programs and the data in files. That's what they're for. They are simple text processing tools. Let's have a look at some common filters. These are used regularly in Unix shell scripting. We have got cat, of course. You may ask yourself what processing is done by cat. Well, none, really. You could say that it's the no processing filter. Whatever input it receives, it just puts it straight back out to the screen. And yes, of course, because cat is a filter, it is possible to type cat by itself on a line with no parameters, and it will just sit there waiting for input from the keyboard, and whatever you type, it will echo back out to the screen. More is, of course, a filter which does exactly what cat does, except it does it one page at a time, so we've got pagination happening. grep, we'll look at grep a little bit later on in this chapter, and sort, we'll also look at sort later on in this chapter. We've had a look at WC already. T, we won't really have a look at that, but it provides a nice little facility to write information both to a file and to the screen at the same time. And then sed and awk are actually very powerful filters, and I'll spend a bit of time in this chapter explaining the use of both of them to you, because they are both tools that you really need to become familiar with if you want to be a proficient shell programmer. So for the rest of this chapter I will be explaining to you the following programs: grep, sort, sed and awk, and I'll also be having a little discussion about what a regular expression is, because you do need to know. So that's what the rest of the chapter looks like. Let's move on. The first filter that we're going to have a look at is grep. Now, grep is a reasonably powerful program. You've probably used it before in some simple way. I'm mainly showing you grep in this particular chapter so that I can show you what a regular expression is, but that's next. So first let's have a look at the simple usage of grep. In its simplest form, it simply displays lines of text from its input that contain a certain pattern. Recall that its input will either be from the keyboard or from another file, or it will be from another program. So you can actually rephrase that in another way. It removes lines of text from its input that do not contain the pattern. That, I guess, would be a more accurate definition of its processing. And because it does that, you can say that it actually filters out these lines of text. So grep is, I guess, the classic filter, in the sense that it is a filter that actually does filtering. You've probably seen it in action before, but I'll show you its usage at the moment. You simply specify a pattern that you wish to search for, and then you can optionally specify the files that you want to look in to find that pattern. Now, of course, if you don't specify any files, then it reads that information either from another program or from the keyboard. For example, you might want to look for the word sincerely in all the files that end in .txt. Alternatively, you can simply take the output of the who program and pipe it to grep, and maybe search for the word root, which would of course just show you all the instances of where root is logged in. Now, as short as it may be, that is in fact the end of this module, but that's not all I want to say about grep. We'll actually be looking at grep in considerably more detail in the module, because the real power of grep comes through its use of regular expressions. So I need to explain to you what a regular expression is and then show you how grep actually uses those regular expressions. So let's do that now. If you've ever wondered what grep actually stands for, it actually stands for Global Regular Expression Parser. So I think it's fair to assume that grep makes strong use of what we call regular expressions. Now, interestingly, grep is not the only program that uses regular expressions. It's actually used quite extensively by other Unix programs, and I'll show you which at the end of this module. So understanding and using regular expressions is an important part of the arsenal of any shell programmer. As a shell programmer, you're really handicapping yourself if you don't understand what a regular expression is or how to use one. So let me show you now regular expressions by using grep as our example. So, what is a regular expression? It is a term used to describe a set of special text matching patterns. So the best way to explain that, I guess, is to show you some examples of those. The text matching pattern caret, or the little up hat symbol, matches the beginning of any line. So caret ABC matches any line of text that begins with ABC. So let's have a look at that in action using grep. I have a text file called sample in the current directory, and I'm going to search in that file. I'm going to search that file called sample for lines that begin with ABC. Now let's see if there are any. So we'll search for grep, and then notice that I'm going to put a single quote around this, caret ABC, and then single quotes. So I've enclosed caret ABC inside single quotes, and then the file called sample. So what I'm actually doing is I'm searching in the file called sample for the pattern caret ABC, which really means ABC at the beginning of a line. So I'm looking for lines in sample that begin with ABC. And let's see if there are any. And there are, in fact, 1, 2, 3, 4, 5. Now that's not all the lines in the file. I'll prove that because I'll do an ls-l of sample, and it is a really large file. It's nearly a megabyte. In fact, it is a copy of the /etc password file from this computer. So if you like, 1, 2, 3, 4, 5 users on this system have their names that begin with ABC. I could just do a search for ones that have ABC anywhere in their name, like this, and I get a few more, 1, 2, 3, 4, 5, 6, 7, 8, 9, roughly 9 or 10. But by putting the caret symbol at the beginning of the ABC, I restrict the search to the ABCs that are at the beginning of the line, which of course enables me to perform more powerful text searching, which is in actual fact what regular expressions are for sophisticated pattern matching. So let's have a look at some more of the regular expression pattern matching facilities at our disposal. ABC $ matches any line of text that ends with ABC. So let's see if there are any of those, and I'll do a little search for them, and there's absolutely none at all. And now what that actually means is that the line does not end in ABC. Typical lines actually from the /etc password file end in the name of the shell that you're using, so we don't have any shells called ABC. So what about if we had a shell called just simply SH? How many people are using just SH as their shell? And there are 6 of them. I put the slash in because I didn't actually want the shell BASH to match that. Okay, so that's the end of the file, which is kind of the opposite of the beginning of the file. So let's have a look at some more. We can obviously combine those two together, and if something begins and ends and there's nothing in between the beginning and the end, then we've obviously matched a blank line. So moving right along, A asterisk matches any sequence of 0 or more A's. I'll show you an example of where you might use that. So if I was to search for CA asterisk T, what I'm actually searching for is either CAT or CAAAT or CAAAAAT, or even a C and a T with no A's in between them whatsoever, because recall that it matches 0 or more of the character immediately preceding it. So what we're actually asking for is a C followed by 0 or more A's followed by a T. So let's see if we find any. Well, there was certainly a bunch. Now I'm just looking at the output here and I can't really see any instances of more than one A, but I can see that there are some instances where it's CAT and there's other instances where it's just CT by itself, like the third one from the top, Tectonic. That doesn't have any A's in it whatsoever. It's just a C and a T with 0 A's in between. Now if you actually want to match at least one A, for example, then instead of using the asterisk sign you use a plus. But the plus is actually not part of the standard regular expressions. It's part of what we call extended regular expressions. And so if you want to use extended regular expressions, you have to use a special option to grep, the -E option. So I'll show you that now. So here's the same example again, only with an asterisk replaced by a plus. And we run that and we get absolutely no results at all. And yet we were expecting some results. We were expecting to see maybe all the CATs. And the reason we didn't see any is because we actually need to specify that this is going to be a an extended regular expression. So what we need to do is put in just here a -E option, E for extended regular expressions. Now I've actually made a little mistake here. It's actually not lowercase e, it's actually uppercase E, so I'll just quickly fix that. I'll put in the uppercase E for extended regular expressions, and this time we in fact match quite a lot. It is a little bit fiddly to know which parts of the regular expressions are extended and which ones are not part of the extended set, but that's, I guess, just part of the joy of Unix. Moving right along, we can use the square brackets in a very similar way that the shell uses square brackets to match file names. Anything enclosed in the square brackets is used to match a single character. So C followed by square brackets followed by T matches C and then any single character from within the square brackets and the T. So C square brackets A O U brackets T matches cat, cot or cut, but nothing else. It will not match CAOT or COUT because it's only trying to match one character. So let's look at an example of that. Now we already know that there are many CATs, but how many OTs or CUTs are there? Well, there's still a bunch, and if you verify for yourself on every single line there's either a CUT or a COT. It is of course possible to combine that and with one of our earlier options and put an asterisk there. Now what that will give us will be a C followed by 0 or more O's or U's followed by a T. So that will of course match the option CT, but will also match COUT or COOUOUT or any combination of O's and U's between the T. So let's just check that, and I guess we'll have to assume that's working. I can't actually see any O's and U's next to each other between the C's and the T's, but I assure you that is what that option does. Now one of the more important regular expression options is just the dot, which matches any single character. So C dot T matches a C followed by any character at all followed by a T. So it could match an A or an O or a U, or it could match a space, or it could match a for, or it could match a question mark, or it could match absolutely anything at all. And that is often used in the following way. You would put a dot star there, which means a C followed by anything at all, and any number of those anythings at all, even 0, followed by a T, which of course translates to a C and a T with anything in between them, even nothing. So if there is a C on the line and a T on the same line somewhere after it, then that will match. So we'll just run that, and there's a great deal of them. And if you maybe pause and have a look at the output that you've got, you'll find there is a C and a T with any number of characters in between them on every single line that you can see. Now, just getting back to the square brackets for a moment, you can actually use a range of characters inside the square brackets, and the range is specified by the first character followed by a dash followed by the second character. So we've got A to Z and then capital A to capital Z and then 0 to 9. So the example you can see in front of you matches 0 or more of any of those characters. So 0 or more letters or digits in between a pair of capital X's. Now that's just a small subset of the regular expressions that are available to you, but that's probably the most common set. If you want to learn more about regular expressions, then look in the man page for grep or in the man page for regexp. But the set that I've shown you so far should suffice you for probably 90% of the regular expression searches that you would ever want to do. So what programs actually use regular expressions? Well, obviously grep uses regular expressions. The program sed, which we'll look at shortly, uses regular expressions. Awk, we're also going to have a look at awk. And even vi and the line-based editors ed and x also use regular expressions. There's even more programs, but they're less commonly used, so I won't mention them here. So the bottom line is, if you ever plan to use grep, sed, awk, and even to enhance your power in using your vi program, it would be a very good idea to learn the basics that I've just shown you of regular expression. Another very commonly used filter in Unix shell programming is the program called sort. Now, as you can probably imagine, the sort filter is simply used to sort the lines of text from its input. Of course, remember that that input can come from a file, or it can also come from another program or even from the keyboard. You wouldn't sort your lines of input from a keyboard very often, but we frequently find ourselves sorting the output of another program. The way you use it is like this. You simply type in the name of the file that you wish to sort, or you can just get the results from another program. Now, it's all very simple and I don't want to go into it too much more here, but there is one very common mistake that novice shell programmers make, and I want to show that to you. They typically do something like this. They say, okay, I've got a file on my disk and I want to sort the contents of it. So at the end of this operation I want that file to be sorted. So they simply do sort of file 1, assuming that the file is called file 1, and then they send the output straight back to file 1. Now, before I tell you why that doesn't work, let's see if we can prove that in fact it does not work. Let's have a look at that now. So I've got a file in this directory called ttt. Let's just have a look at it. It's just a shell script. We had a look at that shell script before, I'm guessing. Actually, no, we didn't. That was just a little experiment of mine. It doesn't matter. So let's actually now sort that file, sort ttt, and here is the output of the sort program, all nicely sorted. I'm going to assume that that is alphabetically sorted. Now, if we have a look at the actual ttt file again, you'll find that the file itself was not sorted. The only thing we saw on the screen was the output of the sort program. It didn't actually modify the ttt file at all. Now that's fair enough, but let's now sort the file and send the output back into the file. So by the time we finish this, we should have ttt being fully sorted. So that's now cat ttt, and it is empty. It's completely empty. Now, why would that happen? What has gone on here? We've obviously lost all our data, and if you try and do this, you will lose all the data in any file that you try and do this to. That's almost guaranteed. So can you think what might have gone wrong here? Well, what actually happens is, before the sort program even starts, the shell has a look at this line and says, is anything interesting or special happening at this point? And the first thing it looks at is the very last greater than sign on the line. It says, aha, whatever program we're about to run, the output is going to be sent to a file called ttt. So what I have to do first is I have to prepare ttt to receive the output of the program, whatever program is going to run. So if there was an existing file called ttt, I'll just erase it. Otherwise, I'll create a brand new file called ttt. Now, there was an existing file, obviously, called ttt. So the shell shell, mind you, not the sort program. The shell actually gets in and erases the contents of TTT and then says, okay, we're all set, ready to go, now let's call that program whatever it was. And the program, of course, was sort TTT. So the sort program is invoked and is set to work on an empty file. And of course it doesn't really have much to do. And that is why you should never perform that type of operation. So what you should do instead is the following. The correct technique is sort file 1 and send the results to another file, some kind of temporary file, maybe call it file 2, it doesn't really matter, and then rename file 2 back to file 1. There is no simpler way of doing it. It might look like there should be, but there isn't. So keep that in mind, not just for sort, but for any filter. If you want to perform processing on a file on your disk, like sorting, but it could be anything else, and after that processing is completed you want the actual file to have been modified, then you have to use this technique. Anyway, that's all I want to say about sort for the moment. Let's move. I'm going to now show you the first of the two very powerful filters that you have at your disposal. The first is sed, the second is of course awk, which we'll see in the next module. Sed, which is short for Stream Editor, is a program for performing basic editing tasks on the output of another program or on a file. So you can think of a stream, if you like, an actual water stream like a brook, and as the water flows past a certain point it is modified in some way. So that's what sed does. It sits there, and as the text goes through it, it modifies that text according to a set of rules that you specify. Now it can do that, as I said, with the output of a program, or it can do that in fact with a file. But just as we saw with the sort program, the actual file is not changed at all. The output is simply produced on the screen corresponding to the changes that you requested. So in other words, the file doesn't change, you just see the changes on the screen. So if you want to change the file, then you have to use a technique like I just showed you at the end of the sort module. Now sed in its most basic form looks like this. You specify an action that you want to perform, and you specify, optionally, you specify the files that you want to perform the action on. And if you don't specify files, then it performs that action on the input from either the keyboard or from another program. Now I'll show you what the actions are in a moment and how you construct an action, but you can actually perform several actions at a time as follows. You can say either sed -e action 1 or -e action 2, or you can take all the actions that you're wishing to perform and put them into a script file and just say simply sed -f of the script file. So what that will do is sed will open up the script file, examine all the actions in it, and then perform all those actions on the given input. Keep in mind when you're specifying these actions is that these actions almost always contain special characters as far as the shell is concerned, and so you probably want to enclose those actions in single quotes to prevent the shell doing things with those special characters. Having said all that, let's now have a look at the actual actions themselves. The most common action is text substitution, and you can even use regular expressions here to search for the text that you actually want to replace. Now here is an example of an action changing foo to bar. Change the first occurrence of foo on each line to bar. So let's have a look now. Because we've seen what an action might be, an example of an action, let's see sed doing its stuff. So I've got a file here called test file, and I'll just cat it onto the screen. Test file, and again it's the contents, or at least part of the contents of my etc password file. So what I'll do now is I will run sed over this file, and all instances of bash I will change to born again shell. Let's see how that works. So I do a sed. Now enclosed in single quotes I have S for substitute, and I substitute this bash for born again shell, like that, and then the closing slash and then the closing quote, and then the file is of course called test file. And now everywhere where there was bash, you can now see Bourne Again Shell. That's a very simple piece of text substitution. Now I'll show you two actions on the same line. We'll do one where it's we'll do -e for that, and then I'll do another one where it's -e, and we'll substitute false for error, if I can spell error right, like that. Now I haven't put any single quotes around that because I don't need to. There's no special characters in there like spaces or asterisks or anything. And this time, instead of the word false, you can now see error on the end of the line there. So that's a simple text substitution, S for substitute, and if you put a G after the end of the second slash there, then it will actually change all the occurrences on each line from foo to bar, otherwise it will only change the first one. It's possible to specify a range of line numbers to restrict the actions of the substitute or any action that you're specifying. You can say, well, I only want to perform the action on 1,10. You see the 1,10 there? That means on lines 1 to 10, they're the only lines that I wish to perform that substitute on. Or alternatively, you could say 40, $. Now the dollar actually means, in this case, the last line of input. So all the way from line 40 to the last line of input, I want you to substitute foo for bar. If you don't specify line numbers, then the actual actions will be performed on every single line of input. Yes, and as I mentioned before, the dollar refers to the last line in the file, or last line in the input, more accurately. The second action, I've shown you one action so far, the action of substituting. Another common action is deleting lines. And that is done like so. Delete lines 11 to 20. That's a very simple one. Or alternatively, if you like, /hopscotch/d. Delete all lines with hopscotch in them. Let's have a look at an example of that. So here's my bash example again, and this time instead of substituting one bit of text for another, this time whenever I see the word bash on a line, I'm simply going to delete that line. So all we'll have left are the lines of the text file that do not contain the word bash. And there they are. You can check that if you like, but there's not a word bash on any of those lines. Now, as you can see, there's actually 100 lines in the file called test file, so what I could do is use sed to delete all but the last two of them. So I'll delete lines 1 to 98. Let's have a look at that in action, and I just get 2 lines printed on the screen. And it's even possible to delete all the lines except for the lines that match certain criteria. So you can say from line 3 to the end of the file, do not delete those lines. So it will in fact only delete the lines that do not fall into that range. In other words, it will delete lines 1 and 2, and that's all. Let's have a look at that in action. This time I'm just going to display 99, $, which means obviously from the second last line in the file to the last line of the file, I do not want to delete those lines. In fact, I just want to delete the other lines. So again, I see exactly the same 2 lines of output as I saw before. Or you can say I do not want to delete the lines of text that have the word ducks on them, for example. And if you think about it, that is really similar to what grep does. If you say grep for a certain pattern, then it will actually delete the lines of text that do not contain that pattern on them. Okay, so that's pretty much all I want to show you as far as sed is concerned. I've only shown you 2 actions at the moment, substituting text and deleting text, but those are the 2 most common actions that people use with sed. There are many, many more actions and options available for sed. You should check the man page. But before we move on to the next module, I will actually show you one very interesting thing that you can do with sed. This is a little file that I wrote called sedscript. It's actually very similar to a shell script. In fact, except it's not a shell script, it's actually a sed script. When you run this program, and it will be an executable script that you can run like any other executable script, instead of being interpreted by the shell program, it will be interpreted by the sed program. So obviously the lines of code in this script should be sed actions rather than shell script actions. So what are we actually going to do? Well, we're going to substitute mvirtue, which is my username, to be the author of this course, and we're also going to delete any lines that we find in the input that contain the string Gumby. So I'll show you that in action. Let's run the Who program, and you can see that in the Who program, right at the end of the Who program, there is mvirtue, which is me, showing my login details, and then also about halfway down the screen there is Gumby. So now we can say Who, and we can pipe that to sed script like that, which is an executable program in its own right, and we get the same output again, but you can see that Gumby is no longer there, and the last line, the mvirtue, has been changed to the author of this course. So that's a very nice little thing you can do there. You can create executable sed scripts in their own right, and you can make these quite sophisticated and quite lengthy. Anyway, keep that in mind, and we'll move on to the next chapter. And finally we come to awk. Awk is probably the granddaddy of all filters. The text processing that you can perform with awk covers, well, just about any text processing you could ever want to do. Awk actually stands for Aho, Weinberger and Kernighan, who are the three gentlemen that created it. It's not just a text processing tool, it's also a full-on programming language in its own right. It supports if statements, loops, functions, and just about every other major feature of a procedural programming language. It's an extremely powerful filter because of this, but it is also consequently probably the most difficult of all filters to master. I was once charged with a development project in awk, and the final program that I came up with was over 3,000 lines long. Now, I'm not going to go into the depth of awk required for such programs. I'm going to just give you the basics that you'd use in a conventional shell script. If I was to go into awk in its own right, we'd probably have another training course, another CD if you like. So its usage is fairly similar to sed as follows. You specify an action and then you specify the files that you want to perform the action on. As with sed and all the other filters, the files parameters are optional, and if you don't specify them, it takes its input from standard input, the keyboard, or another program. Differently to sed, however, the action that you specify is actually specified a little differently. It's a sequence of statements enclosed in curly brackets or parentheses. Each of them is separated from the next by a semicolon. For example, you take the Who program and pipe it to awk, and notice that there is one parameter after awk, which is the one action that we want to perform. The action is enclosed in braces, curly brackets, and all of that is enclosed in single quotes. Now, because it's enclosed in single quotes, things like the $1 and the $2 that you can see there are treated as special characters by the awk program. They're not treated as special characters by the shell. So similarly to sed, you should enclose all awk actions inside single quotes. So in order to understand what's happening here, we're obviously going to be printing something out. We're probably going to be printing out the words is on terminal at some point, but we've got this $1 and $2 and the commas to worry about. So in order to understand exactly what's going on here, why don't we have a look at the output of the Who program in some more depth. So if we run Who, we find that each line consists of a username, followed by some spaces or tabs, followed by a terminal, followed by some spaces or tabs, followed by a month, then a day, and then a time. Now, I was being pretty pedantic, mentioning that things were being separated by spaces and tabs, but that is actually significant, especially when it comes to awk. So this is how we treat each one of these lines. Each one of these lines can be said to be broken up into a series of tokens, and each token is separated from the next by either a space or a tab or a series of spaces and or tabs. And so it's fair to say that on each line we have 5 tokens. One is the username, then the terminal, then the month, the day, and finally the time. Now these 5 tokens are actually numbered by awk, They're not numbered at the moment because we haven't involved awk in this equation yet. We've just used the who program, but if awk was to get involved, each line would be said to consist of $1, $2, $3, $4, and $5. So $2, of course, would be, in this case, the terminal, and $3 would be the month, and so on. So if we were to type in the command line that we just had a look at just a moment ago, and there it is, then we run that, and we get the output displayed slightly differently. $1, as you recall, was the username, and $2 was the terminal, in this case, for example, PTS38, PTS48, and so on. So the command line itself involves a print statement. So what print does is it takes a series of parameters. In this case, there are 3 parameters, and they're separated by commas, $1, and then the next one is just a text string, is on terminal, and then the third parameter is $2. And what print does is it prints out on the screen each of those 3 parameters separated by spaces. So it prints out $1 first, in other words the username, followed by a space, followed by the 3 words is on terminal, followed by another space, followed by the $2, which in this case will be the terminal. I hope you're beginning to see the pattern of how awk works. So to summarize that business about tokens, $1, $2, and $3, and so on are the tokens from each line of input, and by default tokens are separated by spaces and or tabs. Now it's actually possible, using the "F" option to awk, to specify the characters used to separate tokens. For example, here is another awk line, and this time I'm using the "F:" Now that designates the colon as being the token separator instead of spaces and tabs. If you think back to our course project, we're actually using the colon there to separate one field from the next. That's what the F stands for field separator. And if you've ever had a look in the file etc password, which is what we're dealing with here on this line, you'll find that it is also separated from one token to the next by a colon. Let's have a look at that. Here is etc password, and as you can see there's a bunch of fields on each line. There's username, and then that little X is supposed to represent where the password goes, so that's 2, then the user number and the group, that's 4, then their name 5, then their login directory 6, and finally their shell 7. So there are 7 different parameters on the line, and each is separated from the next by a colon. So if we wanted to use awk to tokenize each line of the /etc/password file, we'd need to use the "F:" field separator is colon option to break it up into the various tokens. So once it's broken up that way, we can obviously print out $1, which would be the username, and then a space, and then home, and then a $6, which $6, as I recall, is the user's home directory. So let's have a look at that working in action. Here is a little file that I will actually put on the CD for you called parse password, which parses the password file in /etc, and it's a shell script, so let's run it. Run it like that, and as you can see there's quite a lot of output because we have a very big /etc/password file. Now I pressed Control-C there to stop it scrolling all day, but you can see that it's actually working. For each one, R. Ryan's home dir is /home3/R. Ryan, and so on. And that's all made possible by way of the field separator being specified as a colon. Now it's actually possible to perform different actions on lines that match certain patterns. In other words, you can have one collection of actions for lines that match one pattern, and you can have another collection of actions for lines that match a different pattern. For example, for all the lines that match Australia, that have got the word Australia somewhere in the line, then we just want to print out the very first parameter on that line, whatever that happens to be. If you wanted to specify a different action for a different pattern, then after the closing brace, after the closing curly bracket, you'd put a space and then another pattern, like /England/ and then another set of actions enclosed in braces, and so on. Now these command lines can actually be long, but that's perfectly normal, and I'll show you in a moment how to create actuals that really don't have a command line as such. Anyway, we'll have a look at that in a moment. But before we do that, I mentioned that it's actually possible in awk to perform arithmetic, and you might do it like this. We'd assume here that database is a text-based database that contains at least 5 parameters on each line, and maybe the third, fourth and fifth parameters are numeric. So you could add the third and the fourth one together and divide the result by the fifth one on each line, and that would print out the appropriate answer. So very complex awk scripts, if you want to do many actions at once, then what you might do is put them in a separate file. awk-f script file, input file. It's very similar to SED. In fact, it's almost identical to the SED technique. Now, that script file that you specify does not have to be executable, and it doesn't have to have an interpreter definition on the very first line. The interpreter definition, of course, being that # exclamation mark. Script file in this case is just a straight text file. It is, of course, possible to create a script file that's standalone. Doesn't need to be called with the awk-f option on the command line. I'll show that to you. It's possible to create standalone awk scripts, and this is an example of a standalone awk script. You start with the script interpreter. On the very first line, you specify that this entire script must be interpreted by the awk program with the -f option, and that is, of course, the password option that we had a look at just a moment ago. So I'll actually show that to you. So here is a standalone awk script. Now, this script has actually been made executable, and I've got a script interpreter as the very first line, which will cause this script, this program, when I run it, to actually be interpreted by awk. Now, the last part of the script, which is the brace and then the printf line, I haven't shown you printf yet, but I'll show that to you shortly. That's the part of this probably seen already. All I've done is I've put each curly bracket line, and I've put the print line on a line by itself. What you haven't seen is another set of braces up the top there, following the word begin. And everything inside that first set of braces is a series of statements that is run before the input is even opened for processing. So in here you can do all your initialization. You can print out any headings that you want to print out, you can set up a bunch of variables, and so on. And similarly, if you needed to do some processing at the end, after the input had been processed, you could create another set of curly brackets following the word end in capitals. So the only thing that we're actually doing in the beginning part is we're specifying that the field separator is a colon. That's exactly equivalent to doing a -F colon option on the command line. Now, I won't go into this any more detail, show you this actually running. And now let's run it. It was, I believe, called password2.awk. I've just put the .awk extension on the end only to distinguish it from the other one, to show that this is an actual standalone script, and we'll process the file, etc. password, and of course it's working as we would expect. So naturally that which ended up being about 10 lines long could easily grow to as many lines as you like. Don't forget to end each line with a semicolon if there's more than one statement between a set of curly brackets. So here is an example. Of course, if I took those 2 lines and put them in a file called myawkscript and made it executable, then I could run it in the following way. Now, here's that printf facility that I mentioned just a moment ago. It's actually a slightly more powerful print facility than actually the word print. It's called printf. The F stands for formatting, and it's very similar to the printf function C and C++. It looks like this. Now, actually that entire printf statement that you see there should be enclosed in curly brackets, but we'll just pretend that that is for the moment. I don't really want to go into the ins and outs of printf because it would take quite a long time to explain, probably more than that particular topic warrants at the moment. Suffices to say that there's plenty of documentation about it in the manual pages and also on the internet if you look hard enough. What I will say is that it is possible in this way to specify exactly how many characters wide the printing of each field should be. So here are $6 both being printed out, and that's the %-12s and the %-20s, which specifies that $1 will be printed out in a width of exactly 12 characters. So no matter how many characters there are in each $1, it will be printed out and padded on the right hand side with spaces to a width of 12 characters. And $6 will be printed out in a width of 20 characters. So using this technique, it's actually possible to get output beautifully aligned under headings and so forth. Let me show you what I mean. I'll just modify that script I just showed you. So here it is, slightly rewritten, that awk script that I showed you just a moment ago. I've put in the % minus 12s and % minus 20s, so $1 will be printed in a width of 12 and $6 will be printed in a width of 20. Now, for that to be meaningful, I've actually created little headings here, username and directory. Notice that username is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters wide, and directory is 20 characters wide if you go all the way to there. And because these two lines of code have been created inside the begin set of statement block, they will be printed out once and once only at the beginning of the program, whereas this line here will be printed out once for each line of input. So let's see that in action. We'll run this script % and we'll feed it one parameter, which is etc password, and we better pipe the results to more so we can see the heading. And there you go, username and directory, and it's all nicely formatted as you can see. That's the way you achieve that sort of output using awk. Also note that using printf you actually have to specify that you want to have a new line at the end of the output if you do. And new lines are specified just as they are in C and C++ using the \n. If you want a new line followed by a blank line, then obviously put 2 \n's. Okay, so that's really all I want to go into on awk. You can actually buy entire books on awk, so there's no end of learning that you can do just on that program. It's a very powerful, as you can see, text processing language. But I've shown you the basics that you need to get started with simple shell programming. And that actually brings us to the end of the chapter on filters, so let's now have a look at some exercises involving those. And so here are the exercises for chapter 7 on filters. The first is to give you a bit of practice using grep and also practice using regular expressions. I've created a file on the CD called grep-test, and I'd like you to use grep to find the lines in that file that contain the following patterns. I'd like you to find all lines that begin with a T. Then I'd like you to find all blank lines. Then I'd like you to find lines that have 2 or more A's anywhere in them, and I mean consecutive A's. Lines that have a 2-digit number, 2 or more digit number, so it could be 2 or 3 or 10-digit number. Now this is a little bit of a tricky one. You might need to use extended regular expressions for this. Lines that have the pattern open square bracket x, y in them, but I don't just want to see x, y, I want to see x and y being actual numbers. So that might be 6, 7 or 38, 126 or something like that, enclosed in square brackets. So there's a little challenging one for you. Okay, exercise 2. Write a script that produces the following output. It's really just the output from the Who program with the terminal removed. So see if you can come up with that. Obviously the data that you're processing should come from the Who program, and I'd also like to see the output sorted alphabetically by username, which is not something I've done in a little sample output that you can see there, but I would like to be sorted alphabetically. Finally, let's modify the course project. There's a bit of a gaping hole in our course project at the moment, in that when we print out the names.dat at the moment, it's just a raw dump of what's in the file. But what I'd like to see is have it printed out neatly. In other words, get rid of the colons that separate one field from the next, and I'd like them printed out in surname order, and clearly a nice heading would be appropriate as well. So you're probably going to need to use awk to do that. And you may also, if you want to do that sorting thing using the filter called sort, you might like to check the manual page for sort to learn how to sort by a field other than the start field. In other words, we're going to have, I believe in our names.dat we've got the first name first and then the surname second, and we actually want to sort on the surname, so we actually have to sort by the second field in the file. Now it's possible to do that using the sort program, and you'll need to check the manual page to work out how to do that. If you can't get that bit, don't worry, just make sure that it looks quite neat on the screen when you dump the output. Okay, good luck. Here are the solutions to the exercises from Chapter 7. We'll start by looking at that grep test program. Let's have a look at that. I've actually created one file called grepscript that provides the solutions to all of those exercises, and it's self-commenting. In other words, it puts out a little echo line there just before it shows you what it's about to print. So let's see lines that start with a T. Now you can see that that's just using, it's a very simple one, just use the little caret symbol to denote the beginning of the line, and then a capital T there. Blank lines, as we saw before, are a caret followed by a dollar sign. Probably want to enclose those in single quotes just to make sure that the shell doesn't interfere with that. Lines that have 2 or more A's anywhere in them, that's actually very simple, just double A. Now, lines that have a 2 or more digit number in them. Well, this is actually not that hard. There's 2 ways of doing it. One is you can simply say a pair of square brackets enclosing a digit followed by another pair of square brackets enclosing a digit. So that will match one character and that will match another character, and each of those 2 characters will be a digit, so it'll match 2 digits. Or there's another way of doing it, and this uses extended regular expressions. You can say a digit please, and then you can use the curly brackets. Now I didn't show you this, but it's in the manual page. You can say I want 2 or more, that's what the comma means, 2 or more of whatever I just specified. So I'd be saying in this case 2 or more digits from the file. So I need the -E option for extended regular expressions. I've commented that out because I don't want to see the output twice. And finally, lines that have the pattern XY in them, where X and Y is a number. Now I do need the extended regular expressions here, so I put that in there. Now the first thing I want to match is the actual bracket itself, the square bracket. Now the square bracket is a special character for regular expressions, so I need to put a backslash in front of it to make sure that it is no longer special. So we put backslash square bracket. Now this time we actually do want to see a 1 or more digits, so there's 1 digit, and I'll put a little plus sign which means 1 or more. So 1 or more digits followed by a comma, followed by 1 or more digits, followed by a closing square bracket, and again I need to put the backslash in front to make sure that the closing square bracket character is not treated as special. So let's run this to see if it works. And I might need to pipe that to more. So here we are, lines that start with a T, and as you can see there were a few of them, 4 of them in fact, blank lines, and there were a few of those lines that have 2 or more A's anywhere in them, and there's only 1 of those lines. Lines that have a 2 or more digit number in them, and there were 4 of those, line 10, 11, and vector 3 and vector 4. And lines that have the pattern XY in them, and there were 2 of those. You obviously got to make sure that this line here with the 345 in it doesn't come out here at the end. Anyway, there's a copy of my solution on the CD, so you can verify for yourself that it is in fact working. Let's move on to the next solution. My solution is in a file called format who, and of course we just take the who program, pipe it to sort. We want the output sorted, and then we pipe the results to awk for nice printing. Now awk's going to print it out in the following way using printf. We're going to use the %-15s. Now that %s there corresponds to $1. So $1, which is the username, will be printed out in a field width of 15, followed by the second one, which will be the month. Now that's always going to be printed out in exactly 3 characters, so I don't really need to specify how wide that should be. Followed by a space, and then at least 2 characters wide should be the next field, which is the day of the month, followed by a space, followed by the time. So that's 3, 4, and 5, parameters 3, 4, and 5 there. So let's see if that works. Run that %, and as you can see that is indeed working. So finally, let's have a look at the course project. Okay, so here's the well, not much has actually changed in here. Should be only the part where we display out the text, which is case 2, I believe. So yes, there it is, case 2, show what's currently in the file. Now all of that, as you can see, from there to there is all enclosed in round brackets as it was before, and the entire output is set to more, just in case there are quite a lot of data in the file, so it'll come out one page at a time. So we put out a little heading here. Here are the current contacts in the database, and then obviously a couple of nice lines of heading output to show what the columns are all going to look like. And then we're going to display the line in its correct formatting. We're going to use the -f:, which is here, to specify that the fields in the file are separated from each other by the colon character. And we do exactly the same thing with the sort option, except we don't use the -F option. Now we use the -T option for sort. It's slightly different. And the +1 means we want to sort by the second field. If we actually said, if we left out that +1 option, it would sort by the first field, or if we put a +0, it would sort by the first field. But the fact that we put a +1, it means it's actually going to sort by the second field. Did you manage to extract that information usefully from the sort program manual page? Okay, so we end up with a sorted set of information being passed into awk, and awk prints it out using 14 characters, then 16 characters, then 20 characters, then 15, then 6, and then 5, and the 1, 2, 3, 4, 5, 6 different parameters. So we're just using that printf statement again. So as you can see, this sort of column output is very easily done using printf, but that assumes that you actually understand how to use the printf, so I would read up on it if I were you. It is very useful, and I suppose we should see what that looks like. So we'll run this program now, and we'll view the records, and here are the current contacts in the database, and now you can see the nice heading here, and you can see that everything is beautifully aligned in columns for each one. But let's check, is it sorted by surname? A, D, W, X, Z. Yes, it does appear to be sorted by surname. All the other columns do not appear to be sorted by those. So it looks like it's working, so let's press enter. So how did you go? I hope you got through that. I know that I'm setting deliberately difficult questions, but you can do them in stages, because I figure that if you can get through the exercises that I set, then you've really mastered the topic that we've been